Swayam Prabha. Digital India. Educated India.
Welcome. In this series of lectures, we will be studying about organic chemistry part 3. In unit 1, we will be studying about nitrogen containing functional groups. In the lecture 2, we will be studying about nitriles and isonitriles. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project was sponsored by DTH Swayam Prabha, MHRD, New Delhi. In this session, the various topics that will be covered are given here. We will start our lecture from structures of nitriles. Once we study about the nitriles, then we will move on to preparation of nitriles. Mainly we will be studying about dehydration of nitriles, that is from carboxylics, and we also will be studying about nucleophilic substitution, that means synthesis of nitriles from alkyl halides. Later on we will be studying about reactions of nitrile. So in the reactions of nitrile we will be studying about reduction reaction, and we will also study about what is a Stephan reduction, what is Mendius reaction, what is hydrolysis, what is nucleophilic substitution, and what is Thorpe reaction or Thorpe nitrile condensation reactions. Afterwards we will move on to the next topic, which is the structure of isonitrile. In the isonitrile, we will be studying about preparation of isonitrile, mainly the dehydration of formamides, nucleophilic substitution, that means from alkyl halides how we can prepare isonitriles. We will also be studying about Hofmann isocyanide synthesis. Then finally we will go into the reactions of isonitrile. So we will be studying about reductions, hydrolysis, addition reactions of isonitrile, and oxidation reactions. Welcome to the next session. In this session we will be looking at nitriles in the beginning, and we will also study about isonitriles in the later part. Let us start with an overview of nitriles. So they have a general formula R-CEN, and if you look at the reagents which are generally used for cyanation, we have potassium cyanide, sodium cyanide. These are the two major reagents which are generally used for cyanation reactions. The cyanide ion is actually isoelectronic with carbon monoxide and the molecular nitrogen. So we have a negative charge on the carbon atom. So that's why the negative charge compound here is the cyanide ion. Generally, the cyano compounds are considered as poisonous compound because many of the ionic cyano compounds like sodium cyanide, potassium cyanide are highly poisonous. On the other hand, many of the organic cyano compounds are generally covalent in nature. So the major difference between poisonous and non-poisonous or less poisonous is basically the ionic nature. So the ionic cyano compounds are highly poisonous, whereas the covalent organic cyano compounds are less poisonous. Acetonitrile is CH3CN is the acetonitrile. This is the simplest nitrile compound. This is generally used as a organic solvent in many chemical reactions. If we go back to the cyano compounds history, basically the Prussian blue color, which is the first pigment prepared in 1782, which is generally used to color cloths, paints, inks, textiles, etc., is the first cyano compound identified, and the color is given here. This is generally non-toxic to humans. And of course, many of the foods what we eat also contain various nitrile compounds. These are mainly organic nitrile compounds, so they are comparatively harmless. Mainly the cruciferous vegetables like cabbage, Brussels sprouts, and cauliflower, etc., are some of the compounds or the plants which produce glucosinolate, which on enzymatic degradation produces nitriles. Basically the allyl nitrile is the one which is produced when these compounds, these vegetables undergo metabolism in our body. So the one of the enzyme myrosinase is the enzyme which actually cleaves this compound. Glucosinolate compound is cleaved by the myrosinase enzyme to produce allyl cyanide. So this is one of the cyano compound which is produced within our body when we consume these plants. But since these are non-poisonous, we can consume these foods without any problem. Nitriles have a general formula R-CEN, and here we have a carbon nitrogen triple bond, C triple bond N is present here. And if we write the general structure, carbon is having a negative charge, the ionic species carbon is having a negative charge, and nitrogen is having a lone pair, and this is the resonance structure which we can write for cyanide ion. If we look at this structure, the carbon on the left hand side has 2 electrons and it has 3 bonds. So 3 bonds, each bond is 2 electrons, so total we have 6 electrons, and from the negative charge we have 2 electrons, so total we have 8 electrons on the carbon atom on the left hand side. And if you look at the nitrogen, nitrogen is also having 3 bonds, so 3 into 2, 6 electrons are there, and nitrogen is also having the lone pair, so there are additional 2 more electrons, so total if you look at this, nitrogen also has 8 electrons. So in this species, when the carbon is having a negative charge, we have the octet rule satisfied for both carbon atom and for the nitrogen atom, and also we have 3 bonds are present in this particular ionic species. But if you look at the ionic species on the right hand side, the carbon is having 2 electrons and 2 bonds. So 2 bond is 2 into 2 electron equal to 4 electrons, and there is 2 electrons on carbon. So total if we look at here, we have 6 electrons only on the carbon atom. So this is not following the octet rule. Here there are only 6 electrons present on this particular carbon atom, and when we look at the nitrogen atom, there are 2 bonds are there, so total 4 electrons, and there is a lone pair and another additional 2 electrons for the negative charge is there, so that is 4 electrons. 4 plus 4 total, we have 8 electrons on the nitrogen atom. So the nitrogen has 8 electrons, but carbon does not have the 8 electron, and moreover if you look at the structure, we have 1 bond less. Of course nitrogen is more electronegative than carbon, so the negative charge preferably can stay on the nitrogen atom, but if that happens, this particular structure is having only 6 electrons on the carbon atom, so this is less stable, or the contribution to the resonance from this particular ionic representation is less. So that is the reason for generally for the cyanide ion, this is the most preferred structure. So based on the octet rule and the number of bonds, we can say the left hand side resonance structure is the most preferred or the most stable one for nitrile ions. Let us look at the preparation of nitriles. First we will look at the dehydration reaction, that is carboxylics or R-CONH2 compounds can undergo dehydration to give nitriles. And we can also study, we will also be studying about nucleophilic substitution reaction of alkyl halides. So these are all the 2 major methods for the preparation of nitriles. Let us first start from the amides. So we have seen that dehydration of carboxamide or R-CONH2 is the one we have been talking about. So we have amide R-CONH2, this loses water molecule to give nitriles or the cyanide compounds. Of course nitrile and cyanides are synonyms. So what are the different dehydrating agents people or the scientists generally use, are either it may be P2O5 or PCl5. We can also use thionyl chloride in dry DMF. This is the most economic method, and this is generally used in many laboratory preparations. We can also use trifluoroacetic anhydride and pyridine. The solvent here we require is a dry dioxane is required for this particular reaction. This reaction actually gives a better yield than the thionyl chloride reaction. When the starting materials are little bit expensive or very difficult to make, people prefer trifluoroacetic anhydride and pyridine combination, which gives a better yield of the nitrile compound on dehydration. And there are also other methods like paratoluene sulfonyl chloride and pyridine combination can be used, or heating carboxamides with sulfamic acids, or even heating the amide BF3 complex with carboxylic acid as shown here, all leads to the final cyanide compound. So, here we have the carboxamide. This is treated with the sulfamic acid. When these two are heated, we end up with the nitrile as our final product, and ammonium hydrogen sulfate is formed as a byproduct. Similarly, an amide when treated with the BF3 gives the amide BF3 complex, and this amide BF3 complex reacts with the additional molecule of the carboxamide in the presence of a carboxylic acid to produce the nitrile as the major product. We also get hydrolysis of the amide to the carboxylic acid, and ammonia BF3 complex is also formed. So, in the industrial scale, how cyanides are prepared is quite different from the one what we have seen. In the industrial scale, how people do is basically carboxylic acid and ammonia are heated at a high temperature to produce the ammonium salt, and this ammonium salt when passed over alumina, heated alumina, gives carboxamide. So, this is our starting material for the previous step we have seen, and instead of carboxamide as the starting material, the industrial process generally uses carboxylic acid and ammonia, because ammonia is a gas which is very cheap. So, that is the reason people prefer to use ammonia for the production of nitriles. Carboxamides are little bit expensive, but they are produced in the same process, and the formed carboxamide is again passed over alumina, which loses water molecule to give the nitrile as our final product. Dehydration of aldoxymes using P2O5 or acetic anhydride also gives nitrile as our final product. So, this can be the oxime is given here, this undergoes dehydration. So, these are all the various process, mainly the dehydration process for the preparation of nitriles from carboxamides. And we can also use alkyl halides as the starting material for the preparation of nitriles. So, the primary or secondary alkyl chloride generally they react with the sodium cyanide or potassium cyanide, and this is a very slow reaction. Basically, this is a SN2 reaction, that is a nucleophilic substitution bimolecular, and the halogen atom is replaced by the cyanide. So, one advantage for this process is actually if we start with n number of carbon atoms, we will be ending up with n plus 1 number of carbon atoms. So, this is actually used for the homologation of alkanes. Alkane can be converted to alkyl halide, and then the alkyl halide can be converted to cyanide using this process, and the cyanide can be further hydrolyzed, and we can decarboxylate the carboxylic acid to give the alkane. So, or we can also start with any alkyl halide, and addition of one carbon can be done using this particular cyanide reaction. Primary and secondary alkyl halides actually give a better yield in this condition, and tertiary alkyl halides generally undergo elimination rather than substitution reaction. So, this is one of the limitation of preparing tertiary alkyl cyanide by halogen cyanide exchange reaction. So, otherwise primary and secondary alkyl halide can easily be converted to the corresponding nitrile using this SN2 type reaction. This reaction is called as Kolbe nitrile synthesis. So, RCl is our starting material. This RCl is treated with the KCN to give R-CEN and KCl. Alkyl iodide also can be used. So, if you use alkyl iodide, then the same reaction leads corresponding alkyl cyanide, but here the solvent used is little different. We can use aqueous ethanol. So, even in the case of tertiary alkyl halide, this reaction actually gives a better results, and when we use DMSO as a solvent, that actually increases the yield of this reaction compared to aqueous ethanol. And low boiling nitriles, if they are formed in a particular reaction, they are very difficult to isolate. So, these are some of the limitations of this particular method. And we can also use alkyl sulphate as a starting material for the preparation of nitriles. potassium alkyl sulphate when treated with the KCN gives nitrile. So, this is what given here as the product. Potassium sulphate is formed as a byproduct. Isocyanide, which is also formed in this particular reaction, because when we use KCN in this particular reaction, along with the required nitrile, that is the cyano compound, we also get the isonitrile compound, which is the isomer of cyanide. So, this isonitrile can be removed from the system by hydrolysis reaction. So, hydrolysis of isonitrile gives amine. So, the amine is a basic substance which can be removed from the reaction medium. So, that way alkyl sulphate can be directly used to prepare nitrile compounds. We can also use KCN or ClCN as the reagent for the nitrile compound synthesis. Tosylate, generally the tosyl salts when treated with the potassium cyanide gives nitrile. So, the common the general reaction is given here. So, this R group is the one which is actually getting converted to R-CN, and the potassium actually replaces the R group. R and CN form the bond to get the R-CN, that is alkyl nitrile is formed along with the potassium salt of the toluic acid. Sulfonate salt is formed, and Grignard reagents also when treated with ClCN, that is cyanogen chloride, produces corresponding nitriles, or MgCl is the Grignard reagent here. So, this reacts with the cyanogen chloride as shown here. Here the Mg and Cl2 both together are formed as a MgCl2 as a side product, and R and Cn combine together to give R-CN. So, this is how it's a simple reaction of preparing nitriles, and this reaction is actually useful for preparing tertiary alkyl cyanide. So, in the previous case from the preparation of alkyl halides, we have seen that alkyl halide treatment with KCN or NaCN does not give a good yield for the tertiary substrates, but this Grignard reaction is a much better process for preparing tertiary alkyl cyanides. So, the overall reaction of various nitrile preparation methods are given here. The most common one is from the amide starting material. So, the amide undergoes dehydration using Al2O3 or P2O5 and PCl5 or paratoluene sulfonyl chloride and pyridine, or even in the presence of thionyl chloride to give the corresponding cyanide compound. Alkyl halides can be treated with KCN to give alkyl nitriles, and the Grignard reagent when treated with the cyanogen chloride also gives nitrile compounds. Oximes also can be converted to nitrile compounds. So, this is the overall process, various methods for preparation of nitriles. Let us look at the various reactions of nitrile unit. So, the nitriles undergo reduction reaction. We can use sodium in ethanol, nickel hydrogen, that means Raney nickel and hydrogen, platinum oxide and water, this is Adams catalyst, or lithium aluminum hydride reductions. Like various reduction reactions are possible on nitrile. The reduction of nitrile generally gives amines, and we also are going to study about Mendius reaction. Nitriles can be hydrolyzed using either aqueous acids or bases, or dry acids to either acids or esters. We will see what are the examples. And nitrile also undergoes nucleophilic substitution reaction, and Thorpe reaction is a name reaction which we will be studying at the last. So, what are the reactions of nitrile? The first one is the reduction reaction. So, when alkyl nitriles treated with sodium and ethanol produces amines. So, this is the standard reaction. The cyanide and the cyanide has C triple bond N. This is reduced to, here 2 hydrogens are added, here also 2 hydrogens are added. So, we end up with a primary amine. So, this is a simple reaction. So, reduction of nitriles by nascent hydrogen gives amines, and the secondary amine is also formed as a side product. So, we will look at how a secondary amine is formed in this reaction. Basically, when we use metal catalyst, that reduction is much more efficient, and the reaction actually proceeds via imine formation, and The secondary amines is a major side product formation in this particular case. So we have to use a different catalyst rather than normal metal catalyst like sodium and ethanol. We can also use ranitrile. The use of ranitrile, however, avoids the formation of the secondary amine, which is a side product in this particular reaction. So if you look at the direct reaction, the formation of primary amine, nitriles in the presence of hydrogen with ranitrile actually gives the imine as the intermediate, and this imine can be reduced further to produce the primary amine as a final product. But if we are not using ranitrile as the catalyst, then the reaction may proceed in a little bit a different way. What happens is the imine now reacts with the formed primary amine. So if the reaction proceeds to produce some amount of primary amine, some amount of second imine is also formed in that reaction. So these two react together to produce the secondary amine as shown here. So this is one of the side reaction which produces secondary amine. So the Mendes reaction is a better reaction for preparing primary amine, but it also gives additional byproduct, that is a secondary amine. So to avoid that, we can actually use ranitrile as the catalyst. And the other reductions we are going to look at, the formation of secondary amine can be avoided if we are actually going to use Adams catalyst, that is the platinum oxide and water in the presence of acetic anhydride. This also avoids the formation of secondary amine. So here this is our imine product which is formed. That imine product can be reduced to the amine. So the use of acetic anhydride is very, very important in this particular reaction, because the use of acetic anhydride actually acylates the amine compound. So when the amine is acylated, so what happens is we don't have any more primary amine in this particular system. So if you look at the previous reaction, that is the Mendes reaction, this primary amine reacts with the imine. So these two combine together and they actually react to give the secondary amine. So if you use acetic anhydride, the acetic anhydride removes the amine functionality by converting it into the acetate unit. Once the acetate unit is formed, then we don't have any primary amine to undergo reaction with the imine. So this is how we can actually avoid the side product in this particular reaction. And the reduction of nitrile in the presence of lithium aluminum hydride gives primary amine. So the next one is the reactions of nitrile as hydrolysis reaction. So nitriles can be hydrolyzed using acids or bases. So either acid catalyzed hydrolysis or base catalyzed hydrolysis leads to corresponding carboxylic acid, and in this particular reaction the reaction proceeds via amide as the intermediate. So if you look at the reaction, you will actually see that in the industrial preparation for the amide, what we have nitriles, what we have seen is carboxylic acid can be converted to cyanide. So this is what is the reaction we have seen. What happens, this carboxylic acid is treated with ammonia and we end up with the formation of the ammonium salt, and this ammonium salt is converted to amide, and that amide is then further converted to nitrile. So this is the forward process. That is, in the forward process we were using alumina for removal of water. Okay, this hydrolysis is exactly the reverse of that particular reaction. So here what happens, nitrile is hydrolyzed and the intermediate is converted to carboxamide, and once we have the carboxamide, this loses ammonia to give the corresponding carboxylic acid. So this is exactly the reverse of how we prepared nitriles from carboxylic acid. If we are using aqueous HCl or aqueous sulfuric acid in the presence of alcohol, so what happens is we end up with the ester as the final product. Instead of a carboxylic acid, we are going to end up with the ester as the product. So nitriles on hydrolysis in the presence of alcohol and acid or strong acid condition, especially HCl or sulfuric acid, produces corresponding esters. If we are using hydrochloric acid and nitrile, we have a couple of different conditions. The nitriles, when we are treating with the dry HCl in the presence of anhydrous alcohol, that gives imidic ester hydrochloride as shown here. So, this is a different product. In the previous case, if you are using aqueous HCl, so the reaction is little bit different. If you are using aqueous HCl, we are getting ester as the final product, and if you are using no aqueous condition, that if we are using dry HCl instead of aqueous HCl, we will get imidic ester hydrochloride as our final product. If we are not using alcohol and if you are simply using only the nitrile and dry HCl, we end up with the imidochlorides, corresponding imidochlorides are formed. So, these are all the various products that are produced in the hydrolysis of cyanide. So, if you are using aqueous hydrochloric acid and an alcohol, we end up with esters. If you are using dry hydrochloric acid and alcohol, we end up with the imidic acid hydrochloride. If you are not at all using alcohol and if you are only using dry hydrochloric acid, then we end up with the imidochloride. So, these are all the various reactions of nitriles. If we treat nitrile with ammonia, that gives amidine as the product. So, the NH2 group is actually added to the substrate. So, R-CEN, we have one nitrogen, and we are also adding another nitrogen from the ammonia unit. So, that is how we get this particular compound having a double bond. If it is this is called the imine, and instead of R1, if this is a nitrogen derivative, then we call that as a amidine. Nitriles, when reacted with acid anhydride, gives tertiary acid amide. So, if you use acetic anhydride or similar anhydrides when treated with the cyanide, we end up with the tertiary acid amide. The nitrogen is substituted with 3 acyl units from the anhydride unit. So, nitriles reacts with hydrochloric acid in the presence of tin 2 chloride gives corresponding aldehydes. So, this is also another reaction. So, this is a controlled reduction reaction. Instead of carboxylic acid, the nitrile when treated with the tin 2 chloride and HCl followed by hydrolysis produces corresponding carboxylic aldehydes, carboxaldehydes. If the nitriles are having alpha hydrogen atom and if they are treated with esters in the presence of a strong base like sodamide, that gives a nucleophilic substitution product. So, here there is a hydrogen atom which is present on the nitrile. So, if there is at least one alpha hydrogen on the nitrile, when we treat with a strong base, that is sodamide, this abstract this particular proton, this hydrogen atom, and we end up with the carbanion formation, and this carbanion can react with the esters. This carbanion will come and hit the ester, and this is how the reaction actually proceeds, and the charge reversal step we lose the OR group. So, that is where we have written minus ROH. So, during the charge reversal step, this OR is lost and we end up with the corresponding nucleophilic substitution product as shown here. The next one is an important reaction, that is a Thorpe nitrile condensation reaction or Thorpe reaction. So, this is basically the self condensation of nitriles in the presence of a base, especially sodium, at room temperature to give enamines. So, we have a self condensation happening. Whenever a nitrile has to undergo self condensation, we do need a carbon with alpha hydrogen atom. So, the strong base, that is sodium here used in this particular reaction, abstracts this proton, and then we end up with the imino derivative, and this is getting converted to enamine. See, this is our enamine. We have a ene group. Ene is a double bond and we have an amine NH2 unit. So, when we have ene and amine in the same compound, so these are all called like enamine derivatives. And if we do the same reaction at a very high temperature, we end up with pyrimidine compounds as shown here. So, this is also one of the important reaction for the preparation of pyrimidines. So, the reaction is carried out at high temperature, that is 150 degrees centigrade. If we look at the important nitrile compounds, we have Vidalgliptin is a compound which is having the cyano groups or the nitrile group. So, this is a anti-diabetic drug. We also have other compounds like letrozole. Here we have a 2 cyanide units are present in this compound. This is an aromatase inhibitor. Similarly, milrinone is another compound. This also has a cyanide unit in its, this is also a drug candidate, and this is used as a phosphodiesterase inhibitor. And also there is another drug which is a hypnotic drug which also has a cyanide moiety, and cimetidine and amcetrosol are some other compounds which are important drug candidates which are used for treating either heartburn, peptic ulcer or breast cancers. So, they are given here. So, all these compounds have a cyanide unit. Here this molecule has 2 cyanide unit. So, these are the various important nitriles which are used in drugs. Let us move on to the next topic, that is the isonitrile derivatives. Let us start with our overview of the isonitrile. Isonitrile have a general formula R-CEN, and this is also called as carbylamine compounds. They have a very unpleasant odor. Of course, many of you are aware of what is a carbylamine reaction. So, in the carbylamine reaction, R-CEN, that is isocyanide, is produced. The reagent which is used for isocyanation is silver cyanide, and the isocyanide ion is written here. This is isoelectronic with carbon monoxide and nitrogen. In the organic synthesis, basically isonitrile based multi-component reactions are very common. Passerini 3-component coupling reaction, that means isonitrile, carbonyl compound, carboxylic acid, all the 3 react together to give a condensed product. Similarly, Woogie coupling, that is the Woogie 4-component coupling, also is an important reaction. So, here isonitrile is carbonyl compound, carboxylic acid and amine is condensed together to give a final 4-component reaction product. So, one additional unit, that is amine, is used from the Passerini 3-component reaction that leads to Woogie 4-component coupling reaction. These are extensively used in organic synthesis for preparing various heterocyclic compounds and other derivatives. Of course, along with that, isonitrile can also be used for the modification of biomolecules such as carbohydrate and protein. These type of reactions are called bioorthogonal. Actually, bioorthogonal reactions are very important reactions, and when a compound has more than one functionality, bioorthogonal reaction selectively reacts with one of the functionality. So, that is the beauty of these bioorthogonal reactions, and isonitrile can be one of the source for these kind of bioorthogonal reactions. Let us look at what are isonitriles. They have the general formula as we have seen, R-CEN, and this is represented by N nitrogen and carbon triple bond. Similar to the cyanide, here also we will look at what is the general structure for the isocyanide. The isocyanide can be written as shown here. Here the nitrogen is having a positive charge. If you look at the number of Lewis acid structure, if we are looking at, we have the carbon with a negative charge, that is 2 electrons are present on this carbon, and there are 3 bonds are there. So, 3 bonds gives 6 electrons and 2 electrons from the negative charge. So, put together we have 8 electrons for the carbon atom, and if you look at the nitrogen, there are 3 bonds are there, and there is a lone pair on nitrogen also. So, if you put together all these things, nitrogen also has 8 electrons, and this is a charged structure. Carbon is having a negative charge and nitrogen is having a positive charge. But if you write the other resonance structure in which nitrogen and carbon are not having any charges. So, here in this particular case, the carbon has only 6 electrons, nitrogen has 2 electrons, 2 lone pairs, and there are 2 bonds are also there. So, total we have 8 electrons on the nitrogen atom. And if you compare these 2 resonance structures, the one which is on the left hand side has the octet rule satisfied for both nitrogen and carbon atom. So, this is the most preferred structure, and of course, there is also one more additional bond present in this particular ionic species. The one which we have written on the right hand side, of course, nitrogen has the octet satisfied structure, whereas carbon is having only 6 electrons. So, that is the reason this is a incomplete octet is present for this particular carbon atom. Of course, this compound is neutral or no charge is present, but it also has one less number of bond. So, that is the reason the right hand structure is not the preferred one and the left hand structure is the most preferred one for isonitriles. Let us look at the preparation methods of isonitriles. We can prepare isonitriles from formamide. We can also do nucleophilic substitution reactions of alkyl halides, and we can also prepare isonitriles using Hofmann isocyanide synthesis. So, from formamides, how we can actually prepare? The formamides are basically dehydrated using paratoluene sulfonyl chloride or POCl3 or Burgers reagent in the presence of a base. So, the main thing is we need an acid chloride, paratoluene sulfonyl chloride or POCl3 in the presence of a base such as pyridine or triethylamine gives isonitrile. So, this is the starting material. So, this is the formamide. So, here we have the formamide unit, and this formamide unit actually loses water molecule to give the isonitrile as the product. We can also prepare isonitriles from primary amines. So, this is the famous carboxylamine reactions. So, dichlorocarbene, especially these are formed by the treatment of chloroform with alkali base, that is sodium hydroxide. This converts primary amines to isocyanide. So, this is the standard test for identifying amine compounds. So, this is also called as Hofmann isocyanide synthesis. So, the amine when treated with chloroform in the presence of a base, we end up with the dichlorocarbene as the species. This adds to this amino compound to produce the isonitrile, and sodium chloride and water are produced as the byproduct in this particular reaction. So, this carboxylamine formation reaction is a test for identifying amines, primary amines basically. We can also prepare isonitriles from alkyl halides. Alkyl halides when treated with silver cyanide, here again we are going to carry out a SN2 reaction in aqueous ethanol gives isonitriles. In this particular case, if we are using silver cyanide, we are actually getting isonitriles. If the alkyl halide is treated with sodium cyanide, we end up with nitrile as the major product. So, this is the major thing you have to remember. When we use sodium cyanide, which is an ionic species, that reacts with the alkyl halide to produce R-CEN. But if you are using a covalent one, because silver nitrate, the silver carbon bond is basically covalent in nature compared to sodium cyanide, where Na-C bond is actually ionic in nature. So, here AgCN when treated with Rx gives RNC. So, this is the two different reactions. So, the alkyl halide is the same, but treatment with the sodium cyanide or treatment with AgCN produces two different products. So, if it is a silver cyanide we are using, we are getting isonitrile as the major product. So, this is the one you have to remember all the time. If you are going to prepare nitrile from alkyl halide, use sodium cyanide. If you are going to prepare isonitrile from alkyl halide, use silver cyanide. Let us look at the reactions of isonitriles. The first one is the reduction reaction, then we will also study about hydrolysis. We will be studying mainly about aqueous acids, and there are addition reactions also possible. So, we will study about halogen or sulfur addition reaction. We will also study about oxidation reaction. So, the first one is the reduction reactions of isonitrile. Isonitrile can be reduced by hydrogen to give secondary amines. So, we can use metal catalyst for this particular reaction. So, isonitrile on reduction in the presence of nascent hydrogen produces secondary amine as the product. We have seen this in the previous case also. The hydrolysis of isonitrile produces amine. So, this reaction we have seen as the side product in the formation of nitrile or the cyanide preparation. So, here the same reaction can be used to produce isonitrile. In other words, Hydrolysis of isonitrile by dilute acid produces amines as the main product. If you do the same reaction in the presence of a base, no reaction occurs. So for this reaction to occur, we do need acidic conditions. So hydrolysis of isonitriles in the presence of acid produces primary amines and formic acid is formed. Isonitriles reacts with halogens and sulfur to give the addition product. So isonitrile and halogen gives the addition product as shown here, and when it is isonitrile is treated with the sulfur compounds, we get isothiocyanate as the final product. Isonitrile can also be oxidized to give the corresponding isocyanate. This is isocyanate. So these are all the various reactions of isonitrile. Let us look at what are multi-component reactions. The multi-component reactions basically involve more than two starting materials. If just two starting materials are there, these are normal reactions, but in a multi-component reaction, there are more than two starting materials are actually involved, and they generally lead to a single product. So this is the major advantage of multi-component reactions. Of course, when we talk about multi-component reactions, the theoretical number of products possible when more than two starting materials are involved is actually quite high. But in the case of multi-component reactions, even though we use more than two or sometimes four starting materials, we generally end up with a single product. Say for example, if we talk about Ugi reaction, that is a 4-component coupling, or Passerini reaction, which is a 3-component coupling, generally leads to a single product. So this is the major advantage of multi-component reaction. And another major characteristics of multi-component reaction is all the substrate atoms are basically involved in the final product or included in the final product. Sometimes small units like water molecules are formed as byproducts. So other than that, most of the cases, all the atoms which are involved in the starting materials are generally included or kept in the final product. So these are some of the characteristics of multi-component reactions. And since each substrate modifications or variation leads to a new product in multi-component reaction, this makes actually the multi-component reaction an ideal tool for preparing large and diverse chemical compounds, basically libraries for the combinatorial chemistry. Because when the drug developments are basically carried out, we need to have lots of similar compounds. In those kind of cases, multi-component reaction comes as a real tool, because a single modification, say for example in the Passerini reaction, we are going to use isocyanide. So we can keep on changing the alkyl group and we end up with the new compounds of the final product. Similarly, when we are using a carboxylic acid, the carboxylic acid can also be modified, and each modification of a carboxylic acid leads to another new set of compound. So these kind of changes are possible in the case of multi-component reactions. In other words, we can actually create a library of compounds and we can study all these library of compounds against drug targets. So multi-component reactions are generally used in various drug development or the drug discovery process, and also in the case of complex natural products can also be synthesized using multi-component reactions. Let us look at the next one, which is the Passerini reaction or the multi-component coupling reaction. So in this reaction, a carboxylic acid, a carbonyl compound and isonitrile are the three units which react together to give alpha-acyloxy amide. So this is the final product which we are getting. This is the amide product what we are getting. So here the alpha position we have the acyloxy unit. So this is the acyloxy unit that is present here, and this is the amide. If you look at R-CONH2, if we simply look at this one, this is R-CO, NH2 is a carboxamide. So in the carboxamide what we have is in the alpha position we have the acyloxy unit which is added here. So this is the multi-component reaction where we have the various functionalities. We have the acyl group incorporated here, we have an amide which is present here. So two functionalities are added to this particular product, and that is the reason this is called as a multi-component coupling. And similarly, we have another important reaction which is the Ugi reaction. So, this is an additional unit is added to the previous case. That means we have the carboxylic acid, we have the carbonyl compound, we have isonitrile. So, all the three are there from the previous case. What we have extra is only the amino unit. So, this amino unit is present extra in this particular reaction. So, this loses water molecule, and after a couple of in a single one part reaction we end up with the bis amide. So, there are two amide units are present here. We have CONH2, there is one unit here, and we also have another CONH2 unit, there is another unit. So, we have two amide units are there. So, this compound is called the bis amide. So, this is a example of a multi-component reaction, and this is generally used for the preparation of various drug derivatives and other compounds. So, here are some of the examples of multi-component reactions. So, here I had given a few examples about Ugi multi-component reaction. So, this kind of we have a amide unit which comes from the carboxylic acid which we are using, and this amine unit is another unit which is used in a reaction, and we also have another amide unit here. So, like multiple components are condensed together to form the Ugi multi-component reaction. So, we can vary various substituents. Say for example, in this system we have a amine. So, this amine can be modified to get a new product. So, this way Ugi multi-component reaction can produce a plethora of compounds for drug development. And here is another example of Passerini multi-component reaction which produced this complex product. So, these are generally used in the drug development process, and also there are various isonitriles which are important. So, here we have one compound xanthocillin which is a antibiotic, which is a naturally occurring antibiotic, and similarly we also have dermadine and eudosamine terpene skeletons are also present. These kind of compounds are naturally occurring, and these are also used as antibiotic substances. So, these are some of the important uses of isonitriles. Let us look at the comparison between cyanides and isocyanides. So, we have studied so far about the cyanides and isocyanides. So, let us do a quick review of what we have studied so far. The functional group in cyanide is a CN group, and it is actually connected through the carbon end. That means carbon is connected to the alkyl unit. So, that is why these compounds are called as cyanides. And in the case of isocyanide, the functional group is NC. In other words, nitrogen atom is connected to the alkyl chain. So, we write RNC, that means the alkyl group is connected to or through the nitrogen atom. So, these kind of compounds are called isocyanides. Nitriles are basically polar compounds, and they have high dielectric constants that we have seen earlier also. So, there is a full positive charge on nitrogen, and negative charge is also present on carbon atom. So, due to that these compounds are highly polar, and these compounds show high dielectric constants. Isonitriles have very unpleasant odor. That's they are also called as carbylamines, and the primary amines can be converted to isonitrile in the carbylamine test, and the smell of that very unpleasant odor of the carbylamine confirms that we have a primary amine. And basically the cyanides can be formed from alkyl halides. So, the reaction of alkyl halide with either KCN or sodium cyanide, which is an ionic substance, leads to the formation of nitriles. But the same alkyl halides, when treated with the silver cyanide, produces the isonitriles, because the silver cyanide is a covalent compound. So, the reaction of alkyl halides with the silver cyanide produces isocyanides. And when we do the hydrogenation of cyanide, we end up with a primary amine as our reduced product. In the case of isocyanide undergo reduction to produce secondary amines. And when we hydrolyze cyanide, we end up with a carboxylic acid. These carboxylic acids are formed via amides. So, cyanide on hydrolysis produces amide, which further undergoes hydrolysis to produce carboxylic acids. In the case of isocyanates, when we hydrolyze an isocyanide, we end up with a formamide. Cyanides can be converted into amines, aldehydes and carboxylic acids, whereas isocyanates are generally used in the multi-component reaction. That is what we have seen earlier also. So, the multi-component reaction uses isocyanide as one of the substrate, and we can also the application of cyanide, if you look at various nitrile gloves and polymers have cyano compounds as a starting material. The cyanides can be used to prepare nitrile gloves and polymers, especially acrylonitrile type polymers can be used to prepare various compounds. In the case of isocyanide, there are a few naturally occurring isonitriles as an antibiotic compound which is naturally available. And in the case of cyanides, the ionic cyanides are actually poisonous in nature, whereas the covalent ones are less poisonous. Unlike the inorganic cyanides, the organic cyanides are basically covalent in nature. So, since they are covalent in nature, they are less poisonous compared to the inorganic counterpart, which are highly poisonous. Let us recap the summary what we have studied so far. We have studied about the structure of nitrile. We have seen the various resonance structures of nitrile and where the negative charge resides, that also we have seen. Then later on we studied about the preparation of nitriles, we studied about carboxymides dehydration. So, we have studied about the various reagents like dehydrating agents P2O5, thionyl chloride, paratoluene, sulfonyl chloride and pyridine, etc. we have studied. We also have studied about the nucleophilic substitution of alkyl halides by the cyanide ion, either sodium cyanide or potassium cyanide is used to prepare nitriles. And we studied about the various reactions of nitriles also. What is the reduction reaction? The reduction of nitrile produces primary amines. What is Stephan reduction? The use of tin and HCl we have seen, tin chloride and HCl we have seen. What is the Mendius reaction? What are the hydrolysis of nitriles? The hydrolysis of nitrile produces carboxamide, which on further hydrolysis leads to carboxylic acid, that we have seen. We also have studied about the nucleophilic substitution reaction and Thorpe nitrile condensation reactions we have studied. Later on we moved on to the structure of isonitrile. So, what is the stable structure? The resonance structures we have seen, and what is the most stable structure of the isonitrile also we have studied. Then we studied about the preparations of isonitrile, how formamides can be converted to isonitriles we have seen using dehydration. And we also have studied about the nucleophilic substitution, that means alkyl halides when treated with the silver cyanide produces isonitrile. And we also studied about the Hoffman isocyanide synthesis. Later on we studied about the various reactions of nitriles, that means reductions of nitrile, isonitrile. The reduction of isonitrile produces secondary amine. We also studied about the hydrolysis of isonitriles, the addition reactions of halogen and the sulfur we have studied. We also have studied about the oxidation using mercuric oxide, which produces isocyanate. So, all these reactions we have studied. With that we conclude this session. Thank you.